In this lesson, we're going to cover some of the basics around Hive. We're going to look at the Hive architecture. We're going to take a deep dive into how Hive works, look at a sample query and walk through how it works. We'll look at external versus internal tables and what the big differences are between the two. And we'll also investigate the metastore's purpose and use. And finally, we'll finish up looking at partitions and buckets and how they're used in Hive. The Hive architecture is pretty basic. Up here in the upper right, we have our cluster, and down here in the bottom left, we have our orange client, which is outside the cluster. We can install the Hive client directly on our client, and now we can access the job tracker directly. And when we submit jobs, we can submit them directly into the cluster. Another way to install the service is on a separate machine, where we set up a Hive server or Hue, and this centralized service can be used by a single client or many clients. And in this case, when we submit a query, our client simply submits to the Hive server or Hue via the beeswax or the web interface, or the Hive server 2 via an ODBC, JDBC, or Beeline CLI connection. We can now have additional clients which submit to this one single centralized server. A really great thing about the Hive server 2 is the ODBC and JDBC connections. These connections let us use external tools to interface directly with our cluster. And we can submit JDBC or ODBC queries against this Hive server too. Products like Tableau and MicroStrategy take advantage of this. Hive does require a metastore, and when we're setting it up on a centralized machine, we would put that machine on that centralized machine as well. When we install it on our client, this database would actually exist on our client. The metastore's main purpose is to provide Hive table to HDFS data mapping, so that when we run a query in Hive, we're actually looking up data underneath in HDFS. The metastore does not store any data itself. It simply takes the relationships and maps them onto underlying HDFS data. Let's take a look at the metastore. Here we say that we're running a create table page view statement. This table has a view time, a user ID, a page URL, a referrer URL, and an IP address. We can also include some comments on this table. Here we specify that it's row format delimited, so each individual row is going to be an individual entry, and we're going to say that our fields are terminated by the \T or tab character. Then we also specify a location to some path in HDFS. When we create a table like this, we're creating an external table to existing data that's already in HDFS. So this data in HDFS may look something like this, where we see our view time in actual Unix timestamp, our user ID as 1234, our page URL to the Quick Cloud URL, here we're saying at the top, the referrer URL, which is google.com, and then the final IP address of maybe the client that was accessing it. Here we see that our fields are indeed terminated by tab characters, and again, this is the underlying data in HDFS. So now when I run a Hive query like this, select star from page view, where page URL is like Quick Cloud, that is turned into a MapReduce job, and it returns back at least this row and probably many others. Again, the Hive interpreter simply chains pre-built binaries together into an execution path to run a series of MapReduce jobs that perform the query. We cannot get Java source at the very end of the process. Again, with Hive just chaining together these binaries, there is no Java source which we can use to then optimize and create our own Java jobs. Note that this is exactly how Pig works, including the limitation of not getting Java source. Let's now take a look at a sample query in Hive. This query would run equally well in a regular RDBMS, but here we're saying that we're selecting the category as something called major category, the average of the inventory as the average inventory, from the product table where we have inventory greater than 0. We're also running an aggregation function saying group by inventory where our count of our elements is greater than 1,000 so that we see our high inventory items. We can see here that the syntax was heavily influenced by MySQL, and anybody who's comfortable in that database should be equally comfortable in HiveQL, including things like limit clause. Let's go ahead and click on this link together and take a look at some of the things that Tom White is discussing about Hive. In this chapter 12 of Tom's book, we can scroll down a bit here and see some information about SQL compared to HiveQL. We see, for example, that updates and deletes are supported in regular SQL, but being that HiveQL runs on top of MapReduce, we have no ability to update or delete individual records. We can delete entire tables if we choose, but we can't simply go in and update individual rows. We also see that things like transactions and indexes are not supported in HiveQL. Scrolling down a bit, we can see some of the data types that HiveQL has. We see that we have the common tiny ints, small ints, doubles, booleans, and other primitive types that we expect to see in databases, but we also see some really cool things like arrays, maps, and structure types, which are unique to HiveQL. Again, when we create a table, we can specify the data inside of an individual field is an array, a map, which is essentially an associative array, or a structure, which may even contain data of different types. The primitive types we should all be familiar with, and again, we're just deciding at the table level how we're going to define a type. The underlying data in HDFS needs to match that type, and if the two get out of whack, Hive can throw some errors. Hive will do conversions on data types, and we can do conversions explicitly. Again, I highly recommend that you get Tom's book, The Definitive Guide, and go through all of this information in detail. Let's now look at internal versus external tables. For Hive, internal or Hive managed tables are the default. When Hive uses an internal table, it's essentially saying that it will take over the lifecycle of not only the table itself, but the underlying data. And it stores the HDFS data in Hive Warehouse inside of HDFS. Hive assumes that no other system is using this data, so things like a drop table statement will actually remove the metadata, the mapping itself, and the underlying HDFS data. If you're using an internal table and you issue a drop table statement, your data in HDFS will be gone. You can also specify external tables, and you simply point the location at table create time to some directory in HDFS already. Every file inside of that directory will be used in subsequent queries. Now a drop table statement will only remove the metadata, that mapping of when we say a select statement on a specific table pulls out columns and fields, that maps to HDFS data. Only that link will be broken and the underlying data will still be there. Hive buckets and partitions can be very useful for sampling data and for running queries on subsets of the data. In the case of partitions, Hive can use these to speed queries. The same way that you think of doing typical sharding in databases, Hive can partition the directories below the main table based on one of the columns. For example here, if we have /pageview indicating that's the table, and then we break it down by year and month, only the data for those individual years and months will be stored underneath that directory. And then when we come by and run a query on just that individual month, then it will only run on that subset of the data, and our query will run much faster. Hive buckets allow for efficient sampling of the underlying data. When we create buckets, we break a column into buckets, which are essentially hash partitions on that column. Each bucket will now have a random sampling of data for that field. So for example, if we create 1,000 buckets based on user ID, each one of those buckets should have a roughly equal number of users sampled across the entire data set. And when we run a bucket query, we'll then only sample a portion of the data. This can be very useful for testing our code and checking to make sure that it works against data. Again, in this chapter, we took a high-level overview of the basics in Hive. All these topics are much deeper and go much wider, and there are 4- and 5-day courses strictly on Hive itself. And I highly recommend you get a book and read more about this. And I can recommend the O'Reilly Hive book as a great place to start.